welcome. Today we're going to explore some quadratic graphs, exponential functions. So these are functions that start cruising up really quickly or start dropping off really quickly. Uh, we'll get the basic shape. We'll graph this f of x equals 2 to the x power. Typically, the numbers you're going to want to choose are -2, -1, 0, 1, 2, because it'll give you some good positive and negative figures for you to base it off of. You could, in theory, choose any numbers to substitute in for x. These are nice and easy to work with, and it'll show you the positive and negative versions of stuff, which you're definitely going to want. So we're using the equation on this one. We're graphing 2 to the x power. So if our x is -2, we're going to be doing 2 to the -2nd power. Now remember, when you have negative exponents, you put it under a 1, and then you make it positive. So it'd be 1 over 2 to the 2nd power. Now 2 to the 2nd power is 4. And 1 over 4, let's just get it in the decimal version here, would be 0.25. So our x-coordinate is the -2 that we chose. Whatever you get for your answer is your y-coordinate. So we'll eventually be graphing that. Now we're going to sub in -1 for x. So 2 to the -1st power. Rewrite it, 1 over 2 to the 1st power, which is just 2. And then 1/2 as a decimal would be 0.5. So we put in -1, we got out 0.5. When we substitute in 0, 2 to the 0 power, now anything to the 0 power is just 1. So we put in 0, we got out 1. We put in 1, 2 to the 1st power is just 2. So we put in 1, we got out 2. And when we put in 2, that would be 2 to the 2nd power, which is 4. So we put in 2, we got out 4. So we're going to graph these points here. I'm going to move over to the left. We have -2 and 0.25. That'll be like here-ish. We have -1 and 0.5. That's going to be a little bit higher. We have 0, 1, 1, 2, and then 2, 4. So you'll see it's starting to really shoot up there. It gets really steep. This is what is called exponential growth. So it's going to cruise up pretty sharply from there. Now, as far as the left side, if we were to continue it, it goes on forever in this direction. It'll never touch this x-axis on this particular problem. And that line that it never touches, it just gets infinitely closer to it. It's called the asymptote. So it'll never actually touch the asymptote. Okay, watch the language. Let's try another one. Oh, here, we're just going to see if this shows exponential growth or decay. Now, you really need to focus on the number with the exponent on it. Now, if that number with the exponent is bigger than 1, then it's going to show exponential growth. If the number with the exponent on it is between 0 and 1, that's going to shrink it down. That's going to be exponential decay. So if you look at this one, it's 1.5 to the x power. 1.5 is greater than 1, so this would show exponential growth. Now this one, the number with the exponent is 0.8, which is less than 1, so that would show exponential decay, which we're going to graph some of these in a little bit, but the graph for exponential decay just swoops down into the right, like that. It just drops off pretty quick. So let's look, they have a couple graphs for us here. There you go. So as you go from left to right, this one's dropping down, it's getting smaller. So that is exponential decay. Whereas this one, as you go left to right, is shooting straight up almost. I mean, it's not shooting straight up, but it's getting really steep over there. So that's exponential growth. So let's try this. We're picking out equations that are growth and which ones are decay. Again, the important part is to try to find ones where you're looking at the exponent. So if the number with the exponent is greater than 1, it's growth. If it's between 0 and 1, it's decay. So we're going to circle the ones that are showing growth. If you look here, it's 2 to the x power. 2 is greater than 1. This one is 2 to the x power. Again, it's showing growth. This one is 0.3 to the x power. Now 0.3 is less than 1. So that's going to show exponential decay. Now if you look at this, it's 4/3 to the x power. 4 over 3 is greater than 1. It's 1 and 1/3. So this would show exponential growth. This one is 1/5, and 1/5 is less than 1. So this would show you exponential decay. 2 to the x, obviously 2 is greater than 1. Growth. Now here, we're going to come back to this one. 1.72, greater than 1, exponential growth. 7 over 2, 7 divided by 2 is 3.5, so that's much bigger than 1. So that would also show growth. Now the reason I save this one for last is you would think 2 to the x power would show exponential growth, like this, but because the number in front is negative, it would reflect it. So this one's actually going to look something like this, which would technically be exponential decay. That was kind of a tricky one. So see if you can write any equation that would model exponential growth and exponential decay. So it could be as fancy as you want. Let's say I said, you could say f of x, you could say y, you could say g of x, it doesn't matter. But the important thing is the number with the exponent has to be greater than 1. So we could say 4 times 1.1 to the x power. 1.1 is greater than 1, so that works. Now exponential decay, we could kind of go with the same, we could say y equals 4 times, as long as our number with the exponent is less than 1, greater than 0, obviously. So we could say like 0.999 to the x power. Ooh, that was sneaky. Just a little bit less than 1. We're just so sneaky like that. All right, now here's the general formula for exponential growth and decay. So you have this function here, which is saying like a is a function of time. So time is an important factor here. So a sub 0, this is like your initial amount. You're going to multiply that by 1 plus or minus the rate to the t power. Now t is always time, and usually it's in years, but the rate is a percentage, and that's going to have to be adjusted into a decimal. So if it was 16%, you'd make it 0.16. So if you look here, a 7% increase, think of like 100% plus 7% would be 107%. Written as a decimal, that would be 1.07. Or you can set it up 1 plus 0.7, which is 1.07. That's fine too. 7% decrease, you would just subtract that from the 100%, which would give you 93%. As a decimal, 0.93. Or just do 1 minus 0.07 and get the 0.93 that way. It's all good. Tony purchased a rare 1959 Gibson Les Paul guitar in 2000 for $12,000. Experts estimate that its value will increase by 14% each year. Write a function to model the growth in value for this guitar. And then I threw in a little extra. I said, then find its current value. So the initial amount of this guitar was 12 grand. My goodness. This is showing a 14% increase. So we're going to do 1 plus 0.14, right? That's the 14%. And it's to the t exponent, right? T is the number of years. We're just writing the general formula here. Now 1 plus 0.14 is 1.14. That's the equation they wanted. Now, mean old Mr. Plant says, well, I want to know the value today. So he bought it in 2000. I'm currently recording this video in 2021. I know some of you in the future are like, wow, he looks so youthful. People in 2021 right now are like, yeah, he looks about the same. All right, so it's been 21 years since Tony bought this guitar. So we're going to say 12,000 times 1.14 to the 21st power. Now, we can do this all in our calculator. Let's see. Now, you do exponents before you do multiplication. So 1.14. Of course, there we go. 1.14. Okay, this calculator is fading on me. That must be a sign of what? I don't know. 1.14 to the 21st power. You get 15.66, blah, 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 blah. A lot of numbers. So then I'll just multiply that by 12,000. Holy smokes. Let's see. 188,010.94. 188 grand. Wow. Now, I was giving Tony beef earlier about spending 12 grand on a Les Paul, but it's quite an investment. Now it's worth 188 grand. Holy smokes. All right, the value of a truck bought new for 28 grand decreases 9.5%. So we are going to be subtracting 1 minus 9.5% in decimal form would be 0.095 to the t power. Write an exponential function to show the truck's depreciation, then find its value after 5 years. So just cleaning up this formula, we can subtract here. Or if you did 100 minus 9.5%, that would be 90.5%, which would be 0.905, which is the same thing you would get for 1 minus 0.095 to the t power. So here is our initial formula. Now we have to calculate what it's worth in 5 years. So we're going to be putting in 5 for that exponent. 0.905 to the fifth. So let's put that in our calculator. 0.905 to the fifth power times 28 grand. $16,998.12. Yeah, that's pretty typical for a car. It dropped in value pretty hard those first few years, and then it kind of flattens out, and then, you know. So now we're going to start graphing some of these. This is where it gets exciting. Now we kind of already graphed one of them, but now we're going to dial it up a bit. You know what I mean? So I'm picking the same numbers every time to substitute in for x. They give us a nice balanced graph. So we're doing 1/2 times 2 to the x power. Now this, the number with the exponent, is 2, and that will show exponential growth. So we're going to have to do 1/2 times 2 to the negative second, which we're going to rewrite that as 1/2 times 1 over 2 to the second. And 2 squared is 4. So we have 1/2 times 1/4, which would give us 1/8. And I'm just going to turn it into decimal form. 1/4 is 0.25, so it's 0.125. So our x is -2, our y is 0.125. So we can chuck that on the graph right now. Here's 1/2, here's 1/4-ish. I don't know, there-ish? Yeah, sure. All right, now we'll put in -1. So we have 1/2 times 2 to the negative first. We're going to rewrite 2 to the negative first as 1 over 2. 1/2 times 1/2, 1/4. And decimal form is 0.25. So -1 and 0.25 is about there. When we put in 0, 1/2 times 2 to the 0. Remember, anything to the 0 power is 1. So we have 1/2 times 1, which is 1/2, or 0.5. So we're at 0 and half. Now we're going to put in 1 for the exponent. 1/2 times 2 to the first is just 2, and 1/2 of 2 is just 1. So our coordinate will be 1, 1, and one more. 1/2 times 2 to the second power. 2 squared is 4, and half of 4 is 2. So we go to the point 2, 2. Now zoomed in, this kind of almost looks like a straight line, but realistically, it's starting to slowly curve up. And if this was zoomed out more, it would get much steeper once you go past 2. Like if you were to put in 10, 2 to the 10th power is just an astronomical number, and then you would just take half of that. It would still be huge. Okay? Now this one is 1/2 to the x power, so this will show exponential decay. I'm going to scoot down here. There we go. All right. So we're doing 4 times 1/2 to the negative second power. Now when you have a fraction to a negative exponent, you can flip it and make it to the positive exponent. So you use the reciprocal. So this is the same as 4 times 2 over 1, which is just 2, to the positive second power. Huh? That's fun. So 2 squared is 4. 4 times 4 is 16. So we go to the point -2, 16, which would be way up there. Just keep in mind, it's even beyond our graph. Let's try -1. 4 times 1/2 to the negative first power. Again, if it's a negative exponent on a fraction, just flip it and make it positive. So if we flip it, it's 2 over 1, which is 2. To the first power is just 2. So we have 4 times 2, 8. So -1 and 8. Hey, there we go. We're on the graph, folks. We're on graph. Now I'll try 0. What is anything to the 0 power? 1. So it's 4 times 1, which is 4. So we're at 0, 4. Now you'll also start to notice it always crosses the y-intercept, the y-intercept is that number in front without the exponent. But we'll figure that out eventually. So here we put in the first power. 1/2 to the first power is just 1/2. 4 times 1/2 would just be 2. So we are at 1, 2, 3, 4. 1, 2, 3, 4. And then 1/2 to the second power. Now when you square a fraction, you just square each part. 1 squared is 1. 2 squared is 4. 1/4 of 4 is just 1. So we go to 2, 1, and there we go. So we're ready to draw our line through it. Now it goes pretty steep up that way. And this, remember, will approach the x-axis. It will never technically touch it. The only time it would cross the x-axis is if we have a vertical transformation, which I don't even know if we eventually will in this class, but it could happen. But this is the asymptote. It will never hit that line. 1/3 to the x power. Now think, is this showing you growth or decay? Look at the number with the exponent. It's 1/3, smaller than 1, so this will show us exponential decay. So we're doing 1/3 to the negative second power. Remember, we can flip that fraction, 3 over 1, and make it to the positive second power. 3 squared is 9. So our point is -2, 9. That wasn't even that bad. Now we got to do 1/3 to the negative first power. Flip it, 3, make it to the positive first power. 3 to the first power is just 3. So we have -1, 1, 2, 3. Yeah. To the 0 power, anything to the 0 power is just 1. So 0, 1. Yay. 1/3 to the first power is just 1/3. Now as a decimal, that's 0.3 repeating. So we're at 1 and 0.3 repeating, 1/3 of the way up there to 1. And then we have to square it. 1 squared is 1, 3 squared is 9. 1/9 is like 0.1 repeating. So we'll go to 2, 0.1 repeating is about there. Look at us with our exponential decay. It'll approach that x-axis, but in theory it would never hit it. Now my line got a little wonky right there on the right, but it's okay. We're showing it's never supposed to hit that asymptote there. All right, last one. 3 to the x power. This is showing growth. That number is larger than 1. So we have to do 3 to the negative second power, which you put it under a 1, make it positive. 3 squared is 9. And we just did 1/9 with 0.1 repeating. So we have -2 and 0.1 just barely above that line. 3 to the negative first, you just rewrite as 1/3, which is 0.3 repeating. So a little bit higher. Exactly. Thank you. 3 to the 0 power, anything to the 0 power is 1. 3 to the first power is just 3. So 1, 3. And then 3 to the second power is 9. 2, 9. Show off your exponential growth. I know some of you are probably sad. The notes are done. Sorry. I mean, we'll have more tomorrow.